when I submitted the abstract to present here, I was working for the Protection Engineering Group, and then we've since gone through a corporate merger, so I now work for GHD, which is a full-service engineering firm out of Australia. It's actually the largest engineering firm in Australia. So sorry for the confusion. The work I'm presenting today, I collaborated with Dr. Jim Milky of the University of Maryland College Park. He is the chair of the Department of Fire Protection Engineering. I worked with him during my time for both undergrad and grad school at the University of Maryland, and we're still doing some collaborative work today. So any questions can be directed to myself or to Dr. Milky. Okay. So today we're going to be doing a comparison of some empirical egress data that I collected. This data was funded from NIST and specifically through Dr. Erica Kulagowski at the National Institute of Standards and Technology, and comparing some of the empirical egress data to results of Pathfinder and providing an analysis of how that data compares to each other and maybe why it does and does not compare. So, as a quick overview, this empirical egress data, it's video recordings that were taken from numerous high-rise office buildings across the United States. And the image on the screen is exactly what I saw in analyzing the data. And it's a camera view of stairwell landings in each of the stairs in these buildings. And then during the evacuation, we can obviously see occupants come onto the landing from one of 2 points, from either the door entering onto the landing or from the stairs above. We recorded the entrance and exit time of each of the occupants entering and leaving the landing, and that allows us to do various types of analyses in regards to occupant velocity, occupant flow rate, occupant density, that sort of thing. So again, we have two inflows coming in. We're going to call the blue arrow on the right the stair flow, occupants coming down the stairs onto the landing, and then the blue arrow on the top would be the floor flow, occupants coming onto the landing via the floor. Those two flows would combine into one outflow going down the landing, and that's indicated by the red arrow. So this is very typical of any building evacuation. You're going to get this type of merging event on every stairwell landing throughout a building evacuation. Okay. Just a quick overview. Back when I completed this research, Pathfinder 2011 was the most recent release of Pathfinder, so that's what I used. And I created a sample stairwell geometry to mimic that of the empirical geometry that we just saw. And I conducted the analysis using the Pathfinder steering mode, so not the SFP mode that Pathfinder offers. So speaking of the SFP mode, kind of the baseline for egress modeling or egress analyses is given by the handbook chapter in the SFP handbook, authored by Steve Gwynn and Eric Rosenbaum, most recently in the 4th edition, although there's previous iterations in earlier SFP handbook editions. And as it pertains to merging of occupants, the hydraulic model gives the following equation, and that's essentially saying that the outflow from any transition point, so in this case our transition point is the stairwell landing, is equal to the sum of the inflows into that transition point. And the equation that they give is pretty broad, so it can be used in any number of different transition points along the path of egress. For us, we're looking at the stairwell landing, so there's only 2 inflows, so in this case n equals 2. Okay. So again, the hydraulic model states that the sum of the inflows should be equal to the outflow from a merging event. Generally, what we see though in empirical data is that this is not the case. There is some inherent inefficiency or something going on that creates a situation where the outflow rate is less than the sum of the inflow rates. This is fairly well documented in the literature. There's numerous case studies and validations of the hydraulic model where, in comparison to empirical data, we don't see exactly what the hydraulic model is describing in this case. So for my analysis, I created a parameter to measure how well the hydraulic model actually models what's going on, and I'm going to term that the flow ratio. So the flow ratio is simply equal to the actual outflow rate from a merging event divided by the sum of the inflows and then multiplied by 100. So pretty simple. In a case where the hydraulic model accurately predicts the merging event, then the flow ratio would equal 100. If the sum of the outflows is less than the sum of the inflows, then the flow ratio would be some number less than 100. Very simple. So I used this parameter and performed a flow ratio calculation for well over 100 merging events from the empirical data that we collected. And this is a distribution of that data. So looking at this, again, we'd expect the flow ratio to be 100. At least that's what the hydraulic model from the handbook would call for. Clearly, we have a distribution that's centered well under 100. This data gives us a mean flow ratio of about 75, and the standard deviation window is 23 as shown there. So again, there's a clear disconnect between what we're actually seeing in the empirical data versus what the handbook would call for. And on average, the flow ratio, or the outflow rate, is about 75% of the sum of the inflow rates. Okay, so we've established that we have this phenomena going on in the empirical data. Now we can head over to Pathfinder and see how that handles it. So what I did is I created 20 different merging events in Pathfinder with various numbers of floor and stair occupants. I limited each flow to a maximum of 7 occupants to prevent queuing. Once we get into queuing, we see a different phenomena. And I ran multiple iterations of these merging events. Okay. On the screen here is a brief summary of just some of the events. You can see for each event there's a varying number of floor and stair occupants, and then the corresponding flow ratio is also listed there. From the Pathfinder data, we also see that we have a mean flow ratio that is well under the 100% that the SFP hydraulic model would calculate. Here the flow ratio is about 81% with a standard deviation of around 14. So what does this tell us? We know that the Pathfinder steering mode is qualitatively depicting the same trend that we see in the empirical data. So in the empirical data, there's some inherent inefficiency that occurs where the outflow is less than the sum of the inflows. Qualitatively, Pathfinder is also able to model that. Quantitatively, I believe the numbers are in reasonable agreement. In any case of doing modeling, especially modeling of human behavior, there's a huge degree of error. Generally, there's large variances. Any standard deviation that is, even inside of 50, is maybe reasonable for modeling human behavior. I think the numbers I presented were in reasonable agreement. So that begs the question, why is the flow ratio generally less than 100? And I could probably talk for a few hours on that topic, and there's no definitive answer that I've come up with yet. But a few ideas. There's several theses, one by myself, one by another one of my counterparts at the University of Maryland, that spends a significant amount of time diving into this issue. To summarize it here in a few minutes, my conclusion in the thesis was that the flow ratio has an inherent inefficiency due to an increase in density on the landing. So, and as a merging event takes place, the two flows converge on a landing, and in instances where the flow ratio is less than 100, that is accompanied by an increase in density on the stairwell landing. So if you compare the landing to a storage body, let's say you're doing a heat transfer analysis, you generally have a heat in term, you have a heat out term, and you have a heat stored term within the body. That same sort of thing can be applied to people on a stairwell landing. You have a flow in, you have a flow out, and then you have a storage term. And that storage term is depicted by the increase in density on the landing. Conversely, there are some instances where the flow ratio was greater than 100. You saw that in the distribution. Those instances were marked by a decrease in density on the stairwell landing. So again, there seems to be some correlation between the flow ratio and the density. For more info on that, you can see my work as shown there on the screen. That being said, any questions?
Hi, Hi, Chris. I actually had a question. If you go back to the graph, the flow rate graph, what I'm trying to understand is when you have flow in and flow out, you do have numbers that are over 100%. And how is that the case? Is it because you're looking at samples of, say, like almost a control volume? So you're looking at a specific portion so that some of the people leaving were actually already in, say, that control volume. So the flows out can actually be essentially the sum of A plus B is greater than.
Right. So what I did not describe here is the actual methodology for calculating the flow rate. That's actually pretty detailed, but in short, the flow rate is over a given period of time. So let's just say that we calculated over a 5-second period. If there were occupants that were already on the landing prior to that 5-second period starting, then of course they're going to be counted in the outflow, though they weren't in the inflow. And vice versa. You also see that on the back end, where occupants that were not on the landing to begin the 5-second period were at the end of it, but they had not yet exited. So they would affect the inflow, but not the outflow. Right.
Hi. I have one question because
Okay.
what actually is the main issue in this type of stair evacuation is the merging ratio. Did you have a look at merging ratio? Because I know there are many studies. There is who says that it's 50-50 the merging ratio, and there are other studies that a bit deviate from this. But in modeling, the main thing that probably we should have a look at more than the open calculation, because what you did is an open calculation, not a blind calculation. So you plugged the numbers that you got from the experiments. That I mean, it's good, but it's a sort of a verification. This is not validation. What you did can be a repetition of a known data. So the question is, did you have a look at the merging ratio and how the model addressed this? Because that's the thing I would
Right.
have a look
So in this particular paper, I did not address that. In the thesis work that I did. But there's also numerous papers. Karen Boyce, Ed Gallia come to mind. They spend pages and pages discussing that. But if you do take a look at some of my other work, that is addressed in there. Approximately. That is what I found, yes.
It's really interesting. But did you find, again, it's the same question I had before, did you find a threshold? So a point at which the hydraulic calc overpredicts and underpredicts. So it seems to be related to the density on the landing. And at some point, there's a flip when it becomes less efficient. And the outflow becomes less efficient.
Right. So no, in short, the answer is no. We weren't able to find a specific density point that was, a threshold or anything like that. And the issue that we came up to is it's very difficult to measure density on a landing in a transient environment where there's constantly people entering and constantly people exiting. So one way that we attempted to do that was just looking at the number of people physically on the landing. We also looked at the number of people in the camera view, which would then also account for people on the first few steps in either direction. Let me go back here. So there's many ways to do it, and I think where the research is headed is doing some sort of tracking thing where these are all announced or they're unannounced fire drills, so it's not a true emergency situation. So if you're able to put some sort of tracking device or something on an occupant, then you can have an accurate depiction of what the actual density is at the merging point. I think if we're able to do that, we could develop that density threshold where it's more or less.
No? Okay, thank you very much, Chris. I appreciate it.